challenges you can't hear, please let me know with any of our speakers here today. I'm going to go ahead and let Amy get us kicked off so that we can stay on time.
All right. Hi, everyone. My name is Amy Hawkins, and I work at NAVFAC Exwick in Port Hueneme, California. I'd like to thank you for attending the Open Environmental Restoration Resource Webinar on Bridging the Gap from Remedy in Place to Response Complete. This is the second part of a two-part webinar, with part one being strategies and requirements, and part two focusing on practical examples for moderate and high complexity sites. Both parts will soon be available to view on YouTube. If you visit our website, navfac.navy.mil/go/ERB, you will find links to all of the available past OER2 webinar videos under the training portion of our website. Following this webinar, a link will be available to a short survey. Please fill out the survey as it is our main feedback mechanism and should take less than 2 minutes to complete. Yeah, go ahead and go to the next slide. There we go, and you can see our website there at the bottom if you're not familiar with it already. Before we move on, I want to emphasize the disclaimer on this slide. This seminar is intended to be informational and does not indicate endorsement of a particular product or technology by the Department of Defense or by NAVFAC Exwick. Although every attempt is made to provide the most accurate information, there is no guarantee that any technology or product will be suitable for your site. And as always, participation on the webinar is voluntary. Next slide, please. Here are our speakers today. We have Russell Sarabian from NAVFAC Exwick, Mike Singletary from NAVFAC Southeast, and Pamela Chang from Battelle Memorial Institute. Russ has over 36 years of experience in the environmental field and is currently the manager of NAVFAC Exwick's Environmental Restoration, Technology Transfer, and Central Programs branch. He has been with Exwick for more than 2 years now, and prior to that, worked in the private sector, where he gained experience in implementing various remedial technologies, remedial optimization, and program management. He has a BS in chemical engineering, an ME in environmental engineering, and is a registered professional engineer in the state of New York. Mike Singletary is a senior engineer and technical manager in the Environmental Restoration Program at NAVFAC Southeast, where he provides expert advice and optimization support to remedial project managers, program managers, contractors, and environmental legal counsel on issues related to the ER cleanup program. Mike earned a bachelor's degree in civil engineering and a Master of Science degree in environmental engineering from Georgia Tech. Pamela Chang is a project manager at Battelle Memorial Institute and is based out of Southern California. She's been supporting the NAVFAC UST and CERCLA environmental programs for the past 21 years, specifically to design, install, and operate various remediation systems such as soil vapor extraction, air sparge, vapor intrusion mitigation, permeable reactive barriers, and in situ chemical oxidation and bioremediation injection systems. Before our speakers begin the presentation, I would like to invite Kim Parker-Brown from NAVFAC headquarters to say a few words about the OER2 webinars.
Oh, thank you, Amy. And hello, my name is Kim Parker-Brown. As Amy mentioned, I'm an Environmental Restoration Program Manager with NAVFAC headquarters in Washington, D.C. And we at NAVFAC really appreciate your participation in the OER2 webinar series. We have been providing this webinar series for about 7 years now and are as excited as we were when we first delivered the opening remarks with our first webinar several years ago. We're also excited to see the enthusiasm and feedback that we receive from the ER community so far. This webinar series is for our RPMs, our RTMs, contractors, and many others who support the Navy's environmental restoration program. The goal of our series is to provide a venue for two-way communication from both reaching out to and obtaining feedback from our community members. The emphasis of our webinar series is open sharing information and promoting innovations among our community members. And this can be through our policies, through guidance, tools, technologies, practices, initiatives, and even lessons learned. Feedback from our community members is key to the success of our webinar series. And we also need community members to actively recommend topics or volunteer as presenters. Any topic should be relevant to the restoration program and should not contain any marketing materials. The community member would work with the champion and the community, and the community member would present the topic if it is selected by us to present. So just want you to keep that in mind. Now, today's webinar is part 2 of the original segment, which was presented just 3 short weeks ago, last month on November 18th. And of course, the topic, if you did participate, you may recall, it was bridging the gap from remedy in place, or RIP, to response complete, or RC. And as was mentioned during part 1, the part 1 segment, it's a very important topic for the restoration program. And today we're going to start off with providing a short synopsis of what was presented in part 1 pretty shortly here. But we're glad that you chose to join us for this segment, part 2, and that we will be presenting this time our case studies on our medium and high risk sites, and which we believe will be crucial in addressing our complex groundwater sites. Initially, you're going to hear from Russ Arabian, who's going to provide a short recap of part 1, and then from contractors, as Amy had mentioned, Pam Chang from Battelle, and then our TM, technical manager, Mike Singletary, who works in our Southeast NAVFAC office. So they will talk about implementing these strategies for you all. So with that, let's hear from our first presenter, Russ Arabian.
Okay, well, thank you, Pam. I'm sorry, thank you, Kim. Go and start off with a recap here of part 1, in case some of you may have missed that, or could just benefit from hearing this again. Let me just. Okay, so just want to mention that the overall objective of this 2-part webinar is really to present a strategy for bridging the gap between remedy in place and response complete, really to help meet the milestones for these metrics. And this strategy was developed by the NAVFAC Optimization and Technology Innovation, or OTI, work group. And this work group consists of members from each field engineering command, BRAC, and headquarters. And the mission of the work group is to promote innovative technologies and optimization strategies to help achieve timely and cost-effective response actions that are also sustainable and, of course, protective. And the RIP-RC strategy is meant to serve as a roadmap to help RPMs in the planning process and in estimating the time needed to reach program goals. And the strategy differs based on the complexity of the site. And for the more complex groundwater sites, the strategy includes the use of performance-based transitions. And this concept of performance-based transitions will be illustrated in the 2 case studies that you'll be hearing about today. So here's an outline of part 1 that was presented last month. So we discussed Navy programmatic goals along with the RIP-RC strategies for low, medium, and high complexity sites. Really was an emphasis on the high complexity sites, as those are the ones that really present the greatest challenge in meeting our metrics. We then discussed Navy optimization policy and guidance documents, and introduced the Navy's optimization tracking tool that allows us to better understand the benefits of performing optimization at a programmatic level. Part 1 also included a case study where the RC milestone was achieved for low complexity sites. And this slide is showing the metrics for meeting the response complete milestone. So this DoD goal of reaching response complete for 95% of sites by 2021 has been around for a long time. And while there's currently no update of the DoD goal, the Navy has established a set of goals, as you see in this slide, for response complete going all the way out to FY 2041. Now note that PFAS sites are not included in these goals because there are just so many variables with respect to PFAS sites that just makes it impossible to predict where it will be in the next 10 years. So if we exclude the PFAS sites, the Navy has reached the response complete milestone for 86% of the sites, and that's based on the end of fiscal year 21. So in part one, we presented several figures similar to the one that you see here, showing typical milestones for sites with different levels of complexity. This one is for a moderate complexity site. And note that these timelines that are on all of these figures are based on the experience of the OTI workgroup members. And they're not meant to be goals or requirements, but really meant to serve as a planning tool. Now, this timeline is for a high complexity site, and it includes the additional step of the RC transition, where the transition is from an active remedy to a passive remedy. And the RC transition is important for highly complex groundwater sites where it could take decades to reach the cleanup goals. And for these sites, performance criteria can be established for the active remedy, which defines the point at which protectiveness can be maintained with only a passive remedy in place. So some examples of passive remedies include monitored natural attenuation, natural source zone depletion, or permeable reactive barriers. And achieving response complete transition results in lower cost, as well as having a protective remedy that's sustainable and resilient. So the concept of this RC transition will be illustrated in the following case studies. And with that, I'll turn it over to Pam Chang now to discuss the case study at Camp Pendleton.
Great, thank you, Russ. All right, yeah, I'll be talking about a UST site at Marine Corps Base Camp Pendleton. Here's a quick overview of what I'll be talking about. I'll give you a quick site description, talk about the remedial action objectives, the remedy, the construction of the remedy, summary of the remedial action operations, any monitoring data trends we may see, response complete milestones, significant challenges, optimization strategies, and end with current status. All right, so Marine Corps Base Camp Pendleton is located in San Diego, California. It is bordered on the west by the Pacific Ocean and occupies 125,000 acres of land. And any given day, there's over 60,000 people on the base. And with that many people, there tends to be a lot of vehicles, and vehicles need refueling. And Camp Pendleton has 5 gasoline stations on the base. We're going to be talking about the 22 area gas station site. And the 22 area gas station area is very, very busy. It has multiple uses. It has a lot of industrial activity that support the various activities on the installation. Here's an overall timeline of the major milestones for the 22 area site. The 22 area site is actually comprised of 2 gas stations, the first being the military gas station, that is a diesel refueling site. And the second is the Marine Corps Exchange, or MCX gas station, which is a gasoline site. Those 2 gas stations did report fuel releases in the late 80s, and the Navy came in, performed a site assessment, started groundwater monitoring, did an RIFS. The base replaced the USTs in 1996. And after that, an interim remedial action, which is what I'll be talking about mostly today, came in with soil vapor extraction and air sparging at the source area and downgraded portion. There was a cap written, a work plan, and then the remedial action of an oxygen injection, a biobarrier, and the mid plume and leading edge area of the plumes, followed by monitored natural attenuation. And then finally, response complete in 2016. So the main contaminants of concern were diesel, gasoline, and BTEX. But by the time the cap was written in 2001, the main concern really pivoted to the MTB that was in the groundwater. It was a 3,500 foot long plume. It paralleled the Santa Margarita Basin, which had many water supply wells to the north. The RIOs were developed based on the State Water Resources Control Board using their MCLs for drinking water. Here are the MCLs for BTEX, and as you can see, for MTB, 5 micrograms per liter can be pretty challenging to meet as a project action level. The remedy was implemented in multiple phases. It first started off with interim remedial action, which was the soil vapor extraction and air sparge systems for both gas stations in the source area. And then there were 2 systems installed down gradient of the gas station. So those 4 systems total. And then those were transitioned over to oxygen injection biobarriers at the mid-plume and leading edge areas, followed by monitored natural attenuation. Here are just a couple photos of the sites. On the left, you have an example of the source area SVE and air sparge system. On the right is an example of the down gradient SV air sparge system. And I want to talk a little bit about the first gas station, the military gas station. That system operated for a couple years. It removed over 28,000 pounds of petroleum hydrocarbons. Majority of those were removed in the first 9 months of operation, kind of indicated by that graph below. The Water Board did concur with discontinuing the active remediation and transition to M&A. And for about 15 years, the Navy collected groundwater samples with TPH diesel and BTEX concentrations, reducing to less than reporting limits. And for that reason, the Navy started engaging with the agencies to get no further action. But there was a little bit of a hiccup in the sense that there was some soil contamination in the source area that was known. And for that reason, the Navy in 2012 went in, did a very small soil excavation, about a 10 foot by 10 foot area, 10 feet down, 26 cubic yards, removed that contamination. And after that, the agency granted no further action. And those photos on the right are before and after for the excavation. And here's just a figure of the 22 area. Just wanted to give you a little bit of orientation. So the primary MGS, that's the source area SV location. The secondary MGS system, that's the down gradient portion or down gradient system. And the second gas station system, that's the MCX, that operated a little bit longer. It removed 22,000 pounds of petroleum hydrocarbons. Again, like the MGS, a majority of that was removed within the first 9 months of operation. In 1999, the thermal oxidation system was converted over to carbon, and you can see those carbon filters on the right, those white canisters. And groundwater monitoring performed throughout. And in 2004, those systems were shut down to make way for the oxygen injection biobarriers. And here I've added on the locations of the MCX gas station systems, the primary or source area system and the secondary or down gradient system. All right, and here are the oxygen injection biobarriers. On the left, you have the mid-plume. On the right, you have the leading edge system. We tried to blend in those Conex boxes and to the background as much as possible. And on the bottom, some examples of the mid-plume well vaults, and on the right bottom, what it looks like inside the oxygen injection well vault. Here we have pictures. On the left is the compressor and some holding tanks, and then on the right is an oxygen generator. It was able to produce 99% oxygen, and that was simply done by removing nitrogen from ambient air. Those biobarriers were very successful. They controlled the plume migration, reduced TPH gas and BTEX to below action levels, while still continuing to reduce the MTB concentrations. And here I've added those blue boxes. Those are trying to point to the mid-plume biobarrier and leading edge biobarrier locations. So in summary, the remedial action operations, again, first started off with the SV and air sparge systems, transitioned to the mid-plume and leading edge biobarrier systems, followed by monitored natural attenuation. So because the site is closed, there's no more sampling occurring, so no data trends from any kind of monitoring. And because this is a UST site and not a CERCLA site, there are no 5-year reviews that are occurring for the site. And response complete milestones. So the best milestones you can have, no further action from the agencies, received MGS and no further action in October 2010, and the MCX, no further action in 2016. Significant challenges. So with, I think, many sites, negotiating the cleanup levels with the regulatory agency is always very challenging. This was made more difficult with regulator personnel changes. I could count about 7 changes that I experienced. And starting in 2012, the Water Board started implementing a low threat UST case closure policy. It was actually a really great policy because it made a consistent method of determining if a site is eligible for closure. However, the criteria inside of that policy, our MTB plume did not meet any of those, it did not meet that criteria. So for that reason, the Navy had to find additional lines of evidence to negotiate closure. Another significant challenge, hotspots. I think this is common as well for most sites. For the MGS, I showed you the excavation that occurred because of the soil hotspot. For the MCX, we had a hotspot of groundwater for MTBE. And so for a couple years, we brought in a portable sparge system, connected it to 3 wells, sparged for 2 years, and we're successful in reducing that hotspot from 820 to 18 micrograms per liter. Remedy optimization strategies. So the main one was in 2007, the Navy performed a third-party optimization, and the recommendations that came out of it were increasing the leading edge oxygen injection barrier system cycling. So just putting more oxygen in the ground, shutting down the mid-plume oxygen injection biobarrier system. Around that area, the concentrations had decreased to almost action levels. And so it made sense to try and shut down the system, and that was achieved in 2010. Optimize the groundwater monitoring program, which was essentially reducing the number and frequency of groundwater wells sampled using regression trend analysis and decision tree diagrams, and then updating the conceptual site model. The regulatory agency indicated there were some data gaps, and so we used cone penetrometer testing to identify those data gaps. So I'll talk a little bit more about the additional lines of evidence used to achieve response complete. I mentioned that the mid-plume was shut down, and that was a lot had to do with doing a sustainability analysis using SiteWise, which is a Navy program, Excel program available on the website. And essentially it tries to quantify the energy requirements of the system or the site and determine the environmental impact of that site. In this metric, we're going to use the carbon footprint CO2. And so the end result being running the mid-plume biobarrier for 1 year is equivalent to driving 16 SUVs all year. And the agencies were very receptive to this, and for that reason, agreed to shutting down the system. Another thing we did was we optimized the groundwater monitoring program. We used regression trend analysis and decision tree diagrams. I don't expect you to be able to read this figure, but the main concept being we categorized all the wells on the site by function, whether they're a century well, a performance monitoring well, a centerline well, and determined should they be sampled annually, semi-annually, or quarterly. And then looking at that data from those wells over time and seeing if those concentrations, for example, decrease with decrease or increase, and if they decrease, to be able to kick them from a quarterly sampling frequency to semi-annually or to annually or to not at all. And this was a really great approach because immediately we were able to reduce the annual well count from 156 wells to 105. And then by the time the site was closed in 2016, the annual well count was 34. And this was a great tool because we put this in the work plan. This was in every groundwater monitoring report. And so we didn't have to negotiate every time we wanted to move a well from semi-annual to annual or remove it completely from the program, because the agency was already aware of it and had agreed upon this decision tree diagram. Another thing we did was the cone penetrometer testing I mentioned. It's a data gap analysis tool that we used to eventually install groundwater wells in the deeper aquifer. We sampled those wells to confirm that no MTBE was down there and that none had migrated vertically. This was a great concern for the agencies, and we were able to complete that data gap. Another thing we do, which I think agencies often ask, is to do a correlation between the MTBE and groundwater elevation. We did that with statistical analysis, and the end result was that we did not find a correlation between groundwater elevation and MTBE. That was very encouraging and helpful towards achieving response to complete. And then lastly, we did a capture zone analysis using ModFlow, a commonly used groundwater monitoring tool in our industry. And we did a 20-year backward particle tracking analysis using various pumping scenarios, like the current pumping rates and increased pumping rates, even to the point where we're drawing down the aquifer and drawing it down to see if the MTBE would be pulled into the production well that supplies all 60,000 people on base. And the end result was there actually was not a draw of the MTBE into the capture zone of the production wells. And I think that was probably one of the key linchpins in achieving response complete for this site. So the current status, the Navy achieved the ultimate goal of returning this area to Marine Corps Base Camp Pendleton so they can complete their mission critical activities. And we achieved no further action. However, the Water Board did note that if there are any future land use changes, they may require reevaluation. And that simply means that if there's any land use changes or construction that is being performed on site and they encounter contamination, that the environmental security people of Camp Pendleton would notify the Water Board to determine if the site needs to be evaluated. And that is my last slide. All right, so I will turn this over to Mike Singletary to talk about his case study.
All right, thanks, Pam. So I'm going to talk about, for the second case study, a site at former mcgregor. I'm going to talk specifically about Area M and the path, including a lot of optimization work that this site has been on to achieve response complete. So mcgregor, this was a large facility, about roughly 9,700 acres, that's located in a fairly rural part of Texas. But it was a government-owned, contractor-operated facility that was used to manufacture bomb and rocket motors. And as part of that process, whenever they would clean those rocket motors out, they would use a hog-out type operation that involved a lot of use of water and chlorinated solvents to clean these motors. So a tremendous amount of perchlorate was released at not only this site, but a number of sites across the facility. So there are a lot of very large perchlorate plumes at McGregor. This city was transferred to the city of McGregor in the 90s, and a large part of the property has been redeveloped. They have a number of different industrial and agricultural leases that use the property for a variety of reasons. SpaceX actually has a testing facility out at this property. The map on the right here shows the Area M plume. This is looking at perchlorate back in 2001. And this was a plume that was over a mile long. You can see the difference in the shading on the figure shows the property boundary. So a portion of this had definitely left the Navy's property. That darker contour there is the 10,000 ppb contour for perchlorate. And you can see this is a couple years after our remediation system, which was a groundwater collection system, had been in operation, and it's starting to sort of control the migration. But one of the primary risk pathway for this site was the fact that the plume had migrated off site, and it was actually threatening a drinking water supply reservoir. So the Navy, really as part of an early interim action, installed a series of collection trenches There was one trench located right along the property boundary. And then there was another trench that was located along a tributary that sort of goes along the eastern boundary of that plume. And the idea originally was for those to serve as permeable reactive barriers so that the water leaving these would be, free of perchlorate. But the flow rates were just too fast and there was not enough residence time. So they basically turned into collection trenches. So a pump was installed in one of the trenches that was used to maintain the groundwater head to prevent discharge into the springs. And that water was routed above ground and treated in a fluidized bed reactor. And that's how we basically controlled the migration of this plume. And this was a key response action early on because we had to contain it and get our arms around it and prevent, further migration of the plume. And so that was done largely by this pump and treat system. And this is an oblique view of the site here. You can see the property boundary running along that lift station shown in the bottom half of the figure there. And these are just larger lagoons and some of the old soil cells that were used to treat contaminated soil. Those were actually used to hold and store water during the rainy season. But that gives you a sense of, number one, the scale of the site. You can see the industrial operations up toward the top of the photograph, and then just sort of the general layout of the way that the site looks. So one of the key aspects of this site is really a life cycle optimization process that we've used to manage this site, basically starting back in the late 90s when the fluidized bed reactor first went into operation. And so we've started out doing traditional optimization activities such as, adding telemetry and automation to the system when it was first started operating, including LTM optimization. We also evaluated a particular key component of the conceptual site model at this site are the groundwater and surface water interactions. And I'll talk about those here in the next slide, but they were important for both contaminant transport and also for a significant attenuation mechanism, particularly for the portion of the plume that had left the installation property and was migrating down gradient. Another key aspect of this site was being able to reclassify the groundwater at the site from class 2 to class 3. And in doing that, we were able to develop a set of site-specific cleanup criteria that were more lenient than the class 2 standards. We also have a plume management zone, and I'll talk a little bit about those, but those are basically portions of the site where you're going to manage the use of the groundwater through land use controls, including deed notices or any kind of things that need to be transferred with the property. But that allows you to not necessarily meet the cleanup objective within the PMZ, but it allows you to manage the exposure to the groundwater through land use controls. And that's been a real key to managing this site as well. I also did an ecological study back in 2016 looking at the residual risk that may be associated with perchlorate in surface water and how that might have impacted sensitive ecological receptors. We looked in particular at amphibians, and we did that in conjunction with some work that Texas Tech University had done, and that allowed us to look at sort of the site-specific surface water exposure pathway. And then finally, sort of one of the last steps in this is really trying to develop a way that we could transition from pump and treat once we felt like we had sort of reached a point of diminishing returns and transition the site over to a more long-term passive way of managing it. Kind of as we've talked about in the first webinar, trying to bridge that gap between RIP to RC on complex sites where you may have a, many decades long RAO phase. We're trying to get to that transition point where we can go from active remediation to long-term passive. And I'll talk about how we did that here at McGregor. So again, the conceptual model at McGregor, the geology at the site's interesting. The water-bearing unit is a weathered limestone, and above that there's a veneer of soil, maybe less than 10 feet. And so when the rains come during the rainy season, that that soil veneer quickly fills up and becomes saturated. And so you have this situation of streams and tributaries in the property losing and gaining at various times during the year based on when the precipitation occurs. And so you'll have periods of time where the streams are flowing, and in the past, those were carrying perchlorate contaminated water down gradient. So a lot of the plume transport here was really a result of that groundwater surface water interaction. And as that water, as the precipitation stopped and those creeks dried out, that contaminated surface water would infiltrate back into the aquifer. And so you had this sort of, dual way of contaminant transport. Now, after we shut the source off by addressing a lot of the contaminated soil and, of course, cutting off the flow at the property boundary, that flushing mechanism still occurred. And so there's a lot of attenuation that we see in the plume due to that same mechanism, particularly if you look at some of the off-site surface water concentrations of perchlorate. And so this was a real key aspect of the site, and we were able to do basically a mixing study of the site and present this to our regulatory agencies as a way of trying to better understand the site conceptual model. So going back to the original containment remedy that I talked about, again, this started back in the late 90s as some initial, smaller scale pilot studies, and this system was put in full scale within, like a 2 to 3 year time period. But again, it relied on, creating these large trenches that were used to collect contaminated groundwater. And again, that was, all that water was routed above ground to a fluidized bed reactor that was used to treat the perchlorate through a biological reduction process. That water was typically stored on site in those lagoons, and then eventually it was discharged into the tributary that ran sort of along the eastern side of our plume, and we had to meet certain NPDES type requirements for discharge. Along with that, we did some significant treatment of the contaminated soils, which was thought to be one of the primary sources. And so that soil was excavated and treated through land farming and then placed back onto the property. And that was done again back, in the early part of the 2000s. So in terms of how well these things that we've done in the source area and looking at some of the natural attenuation, what effect that has had on the plume is actually depicted in this graph here. So this is a graph not really of the performance of the bioreactor itself. That routinely could treat perchlorate down to the single-digit part per billion concentrations. What this plot shows is concentrations of perchlorate going into the fluidized bed reactor over time. So you can see from basically the late 90s, up until about 2016, 2017, about an order of magnitude reduction in the initial concentration. So and this is on a log scale. So if you were to look at this on a linear scale, you would see that curve starting to flatten out. So at this point, in the 2016 timeframe, we started thinking about, have we reached a point of diminishing returns? Do we need to think about potentially transitioning away from pump and treat and maybe focus more on any residual sources that might be present at the site further up gradient? And so this was one of the first sort of key things to look at when we were thinking about transitioning was, what the concentrations were sort of in the plume over time. And this is basically this water, these samples are collected sort of at the very down gradient part of the plume. So it gives you a good idea of the overall sort of contaminant flux over time, again, what's going into the pump and treat system. And I think it reflects a lot in terms of source reduction, you get a lot of that contaminated soil, and then just that long-term flushing action that I mentioned before. So a little bit about some of the plume management strategies that have been employed for this site. Again, the first goal was really to contain the plume, to try to prevent any further migration, and we did that through the hydraulic containment system that I mentioned. The second key aspect of that was establishing this plume management zone, and within the Texas Risk Reduction Program, or TRP, they allow for the establishment of these plume management zones that again, within the PMZ, it's not necessarily that you're expected to meet the cleanup criteria, but that you control exposure to that. So through land use controls, monitoring, and other measures, we're able to prevent use of that water for unintended purposes like drinking water. So we had a PMZ that included both on-site as well as off-site portions of the property. So we're able to work with Texas A&M University, who was the neighboring, owns the property just south of McGregor, able to establish that PMZ. And then finally, being able to reclassify the groundwater, and this applies primarily to the on-site portion of the plume, based on the low specific yield. If we just tested the actual specific yield of the aquifer itself, it was low enough for us to be able to make that justification. And in doing so, we were able to increase the PCO, or the cleanup criteria, not only for perchlorate, but for all of the contaminants by 2 orders of magnitude. So for perchlorate, this goes from roughly 50 parts per billion up to 5,100 parts per billion. So again, we think this makes sense in this particular setting because, again, we're in a very rural area and we can control the exposure, or we can control exposure to the groundwater. So this is a really good option for this particular site. And then finally, again, I mentioned the ecological study that we had done, and that study showed that up to 8,000 parts per billion, no adverse effects were observed for the for the sensitive receptor, that being an amphibian in this particular case. And so again, getting to where we're going with this particular site, it appears at least that the pump and treat system has sort of reached that point of diminishing returns. I mean, we could run that system for the next 30 years, continue to treat lower level perchlorate in groundwater, but we wanted to evaluate other options because it appears, based on the conceptual model, that the down gradient contamination has decreased now to below concentrations of concern. Could we shut the pump and treat system off permanently and really focus the remaining treatment option further upgrading it to where there's a residual source of around 10,000 parts per billion that is still down within the groundwater? And so we did a pilot study back in 2016, 2017, looking at installing a biobarrier treatment system within this zone, based on the fact that the use of biobarriers had been very successful at a lot of the other sites. And so the idea would be, if this proves successful, we would decommission the pump and treat system and rely on that long-term bioactive zone that we maintain within the source area, and then natural attenuation and that flushing mechanism that I talked about for the remainder of the plume. And so again, we did a pilot study of this process back in 2017 and 2016, 2017. Basically installed 2 rows of bioinjection wells across the plume, and we monitored both up gradient and down gradient. And you can see in these graphs, in the down gradient well, once we injected emulsified oil into those injection wells and created this reducing zone, the perchlorate went down significantly, to less than 10 parts per billion. As well as some nitrate. There's a lot of nitrate in the groundwater as well, due to just agricultural activities in this part of the state. But both those contaminants or constituents were able to be reduced fairly easily. In fact, you can see from the plot, we even generated methane. So we achieved more than we needed to in terms of reducing power. And so during the full scale, we'll sort of have to play with the dosing and the reducing equivalents. But again, perchlorate's a fairly easy compound to grade. And so we were successful in creating a reactive zone. And so the plan now is to scale that up to basically treat that entire 10,000 remaining 10,000 ppb hotspot that I showed in one of the previous figures. So just to summarize here for the McGregor case study, again, we've relied on this life cycle optimization approach for managing this site and really to try putting us on that path to eventually achieve response complete. And there were a number of different approaches and different things that we use to do that. I won't go through them in detail. It's what we've talked about, everything from the groundwater reclassification that allowed for a more reasonable cleanup criteria, to the site-specific ecological risk assessment that we did to look at any residual risk that would be present down gradient where that surface water still has some trace levels of perchlorate. The plume management zone is going to be a very important tool for us moving forward because, again, we'll manage this site through the use of land use controls until we reach the ultimate objective, which again may take many decades for this particular site. And then finally, transitioning this site from active pump and treat, which is an extremely expensive and labor-intensive process, to something that's passive was another key milestone for us. And so again, by doing this transition, this will result in significant cost avoidance. At one point in time, we were spending up more than $1 million to maintain, to operate this system and do all of the monitoring. That's been cut down over the years through optimization. But by transitioning this away from pump and treat, we're basically going to achieve about $16 million in cost avoidance. And again, moving forward, it'll be mainly just replenishing that biobarrier on an as-needed basis, and then M&A monitoring. And so in terms of us actually achieving response complete, once those biobarriers are fully constructed and appear to be operating as designed, which will be sometime next year, that's the point in time where we will claim RC in terms of us meeting that milestone. And so again, this going back to this theme of this webinar, which is sort of achieving or bridging that gap between RIP and RC. Again, that key important milestone for complex sites is that our RC transition. Again, for this site, we could have run the pump and treat system for many more decades. We still would have been treating some mass, but we just felt like we had reached that point of diminishing returns, reached an asymptote in terms of the mass removal. So at that point, we felt like it made sense to transition over to a more passive remedy, and that's what we did with the biobarrier. So again, those will continue to run. Still will likely be a decades-long overall time frame, but we've made managing this site a lot more cost-effective and still maintain protectiveness. And so with that, that's the end of this case study, and I'm going to turn it back over to Russ, he has a couple of concluding slides.
Okay, well, thank you, Mike. To the next slide here. Okay, so before taking questions, I'd just like to summarize the two-part webinar. So in part one, we provided some programmatic information, including the Navy's new response complete metrics and a tracking tool used to monitor the benefits of optimization. We also discussed the Navy's optimization policy and the various guidance documents and other technical resources developed by NAVFAC that are available to the public and to be used by RPMs and contractors to help achieve response complete or response complete transition. In both parts, we presented case studies of sites where a strategy was implemented to help achieve the RC goals. And some of the lessons learned from these case studies are summarized here on these slides. One of the lessons learned was that even for a site that's considered low complexity, and this was presented in part one, can have significant challenges to achieving RC. So applying optimization concepts are really beneficial for all sites. Some of the benefits of optimization during the remedial action operation phase included reducing the O&M cost and reducing the monitoring cost, and also improving the effectiveness of the remedy to help expedite the cleanup to reach a point where we either met the cleanup goals or interim goals that allowed for transition to a passive remedy. We also found that to meet RC or RC transition, very often additional data is needed to update the conceptual site model and to allow for modeling and evaluation of natural attenuation. And then lastly, to help meet the RC goals, it's also important to consider reevaluating the cleanup goals in light of state regulations. In the two case studies discussed today, they were both non-NPL sites, and that really allowed more flexibility with respect to risk-based criteria. If it were necessary to meet more stringent MCLs, then it may take quite a bit longer to reach the RC milestone. But in those cases, it would be important to reach a point where a passive remedy would be protective, such as M&A, and that would trigger this RC transition. So those are some of the lessons learned, and we hope that this webinar just helped illustrate some of the strategies and best practices that can be applied to help bridge the gap between RIP and RC. And as Kim mentioned before, we're always excited to present these webinars, and now we're excited to receive your feedback and questions. And Amy, it looks like we do have some time for some questions.
All right. Well, thank you, Russ and Pam and Mike. Any others who have questions, please submit them now, and we'll go ahead and start with a question for Pam. Do you think the Water Board would have been as flexible if contamination at Camp Pendleton was a chlorinated ethene site?
Yes. There's actually chlorinated solvents in the 22 area, and to my knowledge, that site is still open. And because it's chlorinated, those are, DNAPL, it's dives and goes into the deeper aquifer where the MTB hovered and stayed in the shallow area of the aquifer. And so that poses a greater risk that the agencies, I believe, are keeping more tabs on.
All right, thank you. And the next question is for Mike. Did the Navy have to compensate Texas A&M to implement the off-site deed restriction?
I don't know. I'd have to go back and check specifically if there was. I do know that we do have leases for all those properties where we go in and it allows us to go in and do sampling and any kind of activities associated with our remedial actions. And there is a nominal fee associated with that, just to acknowledge that we're going onto their property. But I'd have to go and check on the deed notice. I don't know if we had to compensate them or not. I don't think so, but I can double check on that and get you an answer.
All right, thank you. Our next question could really be addressed by any of our speakers, I think. It is, this approach focuses on those sites that already have an active remedy. Are there sites where you started with passive remedies and are evaluating going to active remediation?
Yeah, I guess I could think of a scenario where, maybe you had natural attenuation that was the selected remedy, either a standalone or part of a treatment train, and maybe it wasn't working to the level that you thought it was or was in the decision document. That might prompt more active treatment, like if it was a contingency remedy in a rod or something. I don't have any good examples of that where you've had to go back to active treatment, but I could see how that could potentially come into play if you're not meeting whatever performance goal that was established. That could happen. I guess that would go back to what goals that you set in the first place and making sure that those are realistic and revisiting them if you need to, based on changes in risk assessment, land use, that kind of thing.
All right, thank you. Okay, we have more questions coming in here. Has the Navy had success with regulators accepting transition criteria to M&A at other sites, such as reductions in mass flux or plateau levels that represent a point of diminishing returns? Would you like me to read it again?
I think I got it. I'll take a stab at it, and then Russ and Pam can join in. But I think this is still a relatively new topic, these transition assessments. I think in practice for a lot of sites, these haven't necessarily been baked into the original designs. We've just sort of done them as the data have come in, and we've analyzed it and tried to in trying to move forward, we've tried to make those kind of decisions about when to turn remediation systems off and transition to M&A. So we have a lot of experience with that. I don't think there's a lot of experience in getting that into the design documents, the decision documents, possibly, ahead of time before we go out into the field. And I think that's one of the whole areas that there's a lot of work being done, is to try to provide RPMs more tools, whether they be, modeling tools, different kinds of planning tools, to determine at what point in time, based on what metric, whether it be a flux-based metric, an asymptotic type of an approach, concentration reductions, whatever that might be, being able to provide some sort of direction ahead of time, I think, is where we haven't done a lot of that. But hopefully that will change, because I think that'll be the key to this gaining more traction, is it appears to be more, again, put into the original design. I don't know if Russ or Pam, Russ, you might have something you want to add.
Yeah, I'll just add that there are sometimes challenges to gaining approval, and some of the recent kind of guidance documents and fact sheets and technical reports that we came out with that I discussed in part one was really geared towards trying to give you some tools to help evaluate monitored natural attenuation to ensure that it is protective. We don't want to go to a passive remedy unless we're confident that it is indeed protective, and then of course we have to convince the regulators and stakeholders. So we do have some tools that fact sheets and tools that came out to help better utilize monitored natural attenuation, evaluate the kind of incorporating the use of some advanced MBT, some advanced analytical tools that we have to do that, to look at both biotic and abiotic processes. So kind of all these things combined, could really be used to help, and also looking at various new modeling tools. So all of these things together, can help us, first us evaluate it to give us confidence, and then to convince the regulatory agencies.
Just throwing in one more thing, I just remembered. There's actually EPA has 2 adaptive site management active pilot sites, or they're testing out this adaptive management approach at 2 Navy sites, one on the East Coast, one on the West Coast. The one for the Yorktown site was a sort of occurring at the remedy selection phase, and it did attempt to put in some of the decision logic when those transition points would occur between source reduction to M&A. So there is more experience being gained, and it might be interesting to follow that site and to see how that sort of plays out in the years to come. But there was a lot of effort that went into some of that early planning for that the site at Yorktown.
All right, thank you. I think we'll take one last question before we break today, and that is, will this RC transition that you've been describing be considered as a program metric or goal for our program?
Okay, well, I'll start with that. It's not an official metric, like an official Navy metric like response complete. However, it is something that we plan on tracking within the norm optimization module. I discussed that a little bit more in part one. It's going to be on the list of one of the success indicators. So yes, we will be tracking it, but it's not a goal that will similar to RC.
Yeah, kind of consider it more of like an optimization step. It's a goal. So we want to get with these complex sites, because again, there's huge optimization implications there, obviously. But yeah, it's not an official metric, but that'll be tracked in norm, correct? The new norm module will have an option in there to track that. So yeah, it'll be interesting to see these as we move forward.
All right, thank you. Mary, can you move us to the wrap-up slide, please? So I want to remind everyone to please complete the survey that will pop up when you leave the webinar. It should take less than 2 minutes to complete, but it is very valuable feedback for us. Upcoming webinar topics are always going to be announced via the T2 email. If you're not receiving the T2 email, you can put a message in the chat box asking to be added to the list, or if you have my contact information, feel free to reach out. I believe there's also a location on our website that you can go to get added to that email. Thank you all again for attending this OER2 webinar. Thank you to our speakers for all of the preparation and good clarity that you gave us on this topic today. And we look forward to having you back next time. Thanks.